Yay!
Okay, another standard example is called calorimetry. And so what we're going to do is suppose we have some sort of insulated bottle, and I've got 2 kilograms of water in the bottle. This is like the worst drawing of all time. So that's supposed to be water in the bottle. And then I'm going to drop in a chunk of iron. It looks like gold, but it's iron. And it's 4 kilograms and it's hot. So it's 90 degrees. So the idea is that your everyday experience tells you that you're going to lose energy. The iron is going to lose energy, right? It's going to get cooler. And the water is going to gain energy. The water is going to be warmer. I'm just saying that's not maybe, I mean, it's obvious from everyday experience, but is it clear that it has to do that, right? That's related to something called the Second Law of Thermodynamics, which we haven't talked about yet. I mean, could it ever happen that you drop something hot into water and the water just keeps getting colder? And the heat flows the other way, right? Maybe the water gets colder and that block of iron gets even hotter. Is that even a conceivable thing? No. Does it violate rules of physics? Well, that's a kind of an interesting question, and maybe technically the answer is no, but you will never ever see it. So that's something still to come. But let's just take it as given for right now that what's going to happen is that the iron is going to get colder and the water is going to get hotter. Okay, heat in some sense flows from hot things to cold things is the way we usually think about it. Okay, well, if that's going to happen, what's the final temperature going to be? I mean, these things are going to exchange energy until they're both at the same temperature, right? So a long time, if you come back after a day where no heat has left the insulated container, what's going to happen is really in much less than a day is that both of these things, the water and the iron, are going to have the same temperature. So what is that temperature? What's that temperature going to be? Well, the principle is, how you would figure this out is that the amount of energy the change of energy of the water, we kind of know that the water is going to gain energy, right? The amount of energy gained by the water plus the amount of energy lost by the iron had better be the same. In other words, if I add these things together, it better be 0. So that's just energy conservation, really, is what this comes down to. So how do we write the change of energy of the water? Well, we kind of already know how to do that. That's just going to be mass of the water, specific heat of the water. The change in temperature of the water, that's just going to be T final minus T initial water, right? And then the other term, what's the change of energy of the iron? Well, that's just going to be mass of the iron, specific heat of the iron, times the change in temperature of the iron. T is T and T initial iron. T initial, too many I's. Okay. Equals 0. Notice I didn't have to put a subscript on the T final because T final for both is going to be the same thing. That's what we're saying. Okay, so, I mean, all I really have to do is just solve for T final. So the things with the minus signs, move them to the other side of the equation. So on the right side of the equation, I'm going to have mass of the water, specific heat of the water, initial temperature of the water. It's on the other side, so I add mass of the iron, specific heat of the iron, initial temperature of the iron. And now I can collect those terms. On the left-hand side, I still have 2 terms that multiply T final, right? So T final is still going to be over here. Let me skip a step and just divide by those. I factor them out. And that's going to be mass of the water, specific heat of the water, mass of the iron, specific heat of the iron. Okay. I mean, that's it. I mean, that's all there is to it. So if I plug those numbers in, let's see, mass of the water, what's that going to be? 2 times specific heat of the water, 4,200. T initial for the water, what did I say, is 10, right? Mass of the iron is 4. Specific heat of iron, I looked it up, it's like 450. Notice it's a lot less. It's a lot easier to heat up iron than water. It's typical of metals. They have a low specific heat. T initial iron is like 90. Okay, and then I'm going to divide by mass of the water. So this same business, 2 times 4,200 plus 4 times 450. All right, just a bunch of numbers to stick into a calculator. And when you do it, what you wind up with is about 24.1 Celsius. Okay, so when you get an answer, because maybe it's easy to like blow a sign or something or stick a wrong number in somewhere, look at your answer and see if that makes sense. First of all, it should be higher than the initial temperature of the water and colder than the iron, right? It should be in the middle somewhere. So sure enough. And does it make sense then that also it should be a little bit closer to the initial temperature of the water? It kind of makes sense because water is really hard to heat up. I mean, for sure, there's twice as much by mass. There's twice as much mass of iron as there is water, but water is almost 10 times harder to heat up. So the combination of those factors is something like 5. I expect maybe roughly 5 times as much temperature difference for the iron as for the water. And did that happen? Yeah, the water went up, 14 degrees, but the iron cooled off by whatever the heck it is, 66 degrees. I mean, something like 5 times different. So that's at least a reasonable kind of a thing. It should be closer to the initial temperature of the water because water is so hard to heat up. This is in general how you solve calorimetry problems. You start off with an energy budget, a balance of energy, and then you just solve for what it is you don't know. Typically, that's going to be whatever the final temperature is.